So when it comes to hypothesis testing, there's definitely a lot of different things you can do. There's a lot of different methods you could use, like the t-test or the various kinds of ANOVA or Pearson's R. But no matter what kind of hypothesis test you end up doing, there's a few additional things to keep in mind. First of all, there's always the chance you could be wrong. Even if you do everything correct and compute all the statistics and follow all the procedures, there's always a chance for error. Error is always a possibility. Remember, hypothesis testing is it's an inferential process. We call it inferential statistics for a reason. We're making conclusions based on limited data. We'll never be able to have all of the data in the universe, so we always just kind of have to make educated guesses, so to say. We're trying to fill in the blanks. We're trying to connect the dots, and we might sometimes do that improperly. There's always room for error. But when it comes to the errors that can happen, they basically come in two kinds. You have type 1 error, which is when the researcher finds evidence for a result that's not actually there. So it's like the researcher finds a significant difference between two groups, but it's not a real difference. You know, the data looks convincing. The data looks like you found something between these two groups, but it's not real. So to put it one other way, if you find something and it looks real, but it's not, that's type 1. So type 1 is when you're tricked into thinking you found something, basically. And then there's type 2. Type 2 error is when you don't find something that is real. When you do not find evidence of a significant relationship when it actually does exist. So this one just basically means you didn't look hard enough. You didn't use the right methods, perhaps. But the point is you failed to find something that was actually in there. So type 2 error then is when you fail to find something that exists in the data. So here, I know this stuff can be a little confusing. So here's a table that hopefully will make this a little bit easier to understand. So you just need to ask yourself two questions. First of all, does the effect actually exist? Is your null hypothesis true, or is your null hypothesis false? So remember, the null hypothesis means that there is no effect. So if your null hypothesis is true, then you should keep it. You should not reject it. If the null hypothesis is true, do not reject it. That is the correct decision. But if the null hypothesis is true and you reject it, that's a type 1 error. So just think back to what I was saying a moment ago. A type 1 error is when there's nothing there, when there is no effect, there's no significant difference, but you think there is. So that's exactly what this table is trying to show you. You've rejected the null even though the null is correct. So that's type 1. Type 2 error is the result of not rejecting a false null. So if you look over here on the right side of the table, if the null is false, then obviously you should reject it. That's the correct decision. But if the null is false and you fail to reject it, that's that type 2 error. Or to go back to what I was saying earlier, type 2 error is when you fail to find a significant effect that is truly there. So I'm trying to explain type 1 and type 2 error as well as I can, but I know it can be a bit confusing. So just try to remember it like this. If you think you found something, it could be a type 1 error. You could be wrong. If you think you didn't find something, then it might be a type 2 error if you're wrong. But let's go into a little bit more detail about these things. Type 1 error is directly related to your alpha level. I talked about alpha level in a previous video. Alpha level indicates the probability that your test will result in a type 1 error. So if you set your alpha level to 0.05, then you have a 0.05 probability of committing a type 1 error. And if you're concerned about type 1 error, if you want to get your type 1 error to be as low as possible, you can just set your alpha level lower than 0.05. So you might think it would be a great idea to have your alpha level very, very low, because type 1 error can be a really big problem. You don't want to go off reporting results of some great finding you've made if it's not real. But there is a problem with doing that. If you set your alpha level too low, not only are you decreasing the chances of type 1 error, but you're actually increasing the probability of a type 2 error. So it's a trade-off. And if you set it so low that you don't find an effect that exists, you probably will not be able to get that published. You'll probably just have to put that away and start over. You know, you believe you failed, but it might just simply due to your alpha level being too low. This is something we call the file drawer problem. The file drawer problem occurs when researchers get non-significant results, perhaps due to that type 2 error I was describing. And when researchers get non-significant results, they typically do not publish them. They do not even try to submit them for publication. And if they don't submit those for publication, then people aren't going to read about it. People aren't going to know what you did. They aren't going to know about the method you used. They aren't going to know about the data you found. And there's reason for this. There's a reason why it's set up this way. You know, nobody wants to read a big long research report and look at all the methods and look at all the data, and then the end conclusion is, you know, we did all this stuff but we didn't find anything. That's really dissatisfying. That's just not interesting. Nobody wants to read that. People are much more interested in looking at positive results. But when people only report the positives, we don't get to see the bigger picture. We don't get to hear about all those interesting failures. Like, researchers throughout the history of science have been trying to do certain experiments time and time again. And if we don't hear about what we're doing, we might end up just making the same mistakes. In fact, that's exactly what's been going on. And there's a lot of discussion in the scientific community about how to deal with this file drawer problem. We need to be aware of what kinds of stuff other people are doing so we don't repeat those same mistakes. Now, alpha level is directly related to your probability of committing a type 1 error. Statistical power is related to type 2 error. Statistical power is the probability of rejecting the null given the sample size and expected relationship strength, and we typically write it as 1 minus beta. So just think of it this way. Alpha level is type 1, beta is type 2. It's a good way to keep those in mind. So when it comes to statistical power, there's a few basics you should understand. Like, the larger your sample, the more power you'll have. And you need higher amounts of power to find weaker relationships between variables. And just in general, the higher your power is, the lower the probability of committing a type 2 error. So going back to what I was saying earlier, when you lower that alpha level, you're actually increasing the chances of a type 2 error. But you can compensate for that by also increasing your sample size. So if you have a very low alpha and a very high sample size, then you'll have low chances of type 1 and low chances of type 2 errors from occurring. You'll actually be able to find what you're looking for in most cases, assuming you did the research correctly. Now, I've shown you formulas for various things, like formulas for, at t-scores and f ratios and r's and whatnot. But I can't really give you a formula for power. Power is a bit more confusing than a lot of these other statistics we've talked about. So instead, I will just provide you with a few links in the description for this video to some online websites that can be used for computing power. It is something that we can use our software to do for us, and it's something that really is far too complicated and not really commonly done by hand. So I don't really need to go into any more detail about it besides that. It's just whenever you're using statistical software, there are ways to compute the power for your test to figure out exactly how much statistical power your study has. And that is an important thing to calculate. You want to be able to find out exactly what are the chances of your study of committing that kind of type 2 error. But besides type 1 and type 2 errors, there's a few other considerations that I just wanted to briefly mention. Doing these kinds of hypothesis tests where we assume that null is correct and then we try to prove it false, this is the standard. This is the most common way we do science. But there are other ways to do this too. I've mentioned previously that a lot of these, methods that we use are kind of arbitrary. Like, there's no real reason to have a p-value of 0.05 be the cutoff, but that's just what most researchers do. It's just the most common approach. But in recent years, these kinds of arbitrary decisions have come under a lot of criticism, and new methods have been developed. Like, for example, the APA, the American Psychological Association, they in fact convened a task force to try to answer a lot of these criticisms that null hypothesis testing has been getting. And those criticisms are, first of all, a lot of researchers don't seem to understand these hypothesis tests that they're using. Secondly, the logic of null hypothesis testing is arbitrary, as I mentioned. There's nothing really special about a p of 0.05. That's just an arbitrary decision. And then third, rejecting the null hypothesis isn't all that informative if you actually think about it. So I wanted to go into a little bit of detail about each one of these criticisms and what the APA has decided we could do to try to solve them. So when it comes to the fact that a lot of researchers don't seem to understand what they're doing, well, we have developed methods such as using confidence intervals. Now, a confidence interval is pretty much exactly what it sounds like. It's an interval. It's a range of values. So this is a range of values around which a statistic is computed so that a certain percentage of the time, usually 95% of the time, the population parameter will fall within it. I know that's a little confusing, but basically what we're saying is with confidence intervals, we're not trying to see if there's a relationship between this and that, or see if there's a difference between this and that. We're just trying to find like a range in which we think the population parameter sits. That's all. So that's one way that we've tried to address this this concern that researchers don't really seem to understand what they're doing, because confidence intervals are a bit more logical. If you really get into them and try to wrap your head around them, they do make a lot more sense. They're not just these weird celestial teapot kind of logical philosophical things. When it comes to this logic of hypothesis testing being arbitrary, the APA style has recommended the use of what we call Bayesian statistics. So Bayesian statistics is a bit complicated, but I'll try to explain it as briefly as I can. It's just a statistical approach in which the researcher specifies the probability that the null hypothesis and any important alternative hypotheses are true before they conduct the study. So what I'm saying here is the researcher, before they do any research, they try to make a prediction about which hypotheses are most likely going to be correct. And then as the study goes, they update those probabilities based on their data. So that's the short version. It's just you make this kind of prediction and you update it as you go. That's the whole idea of Bayesian statistics. And then that last concern, that last criticism, I mean, is that rejecting the null hypothesis isn't very informative. Well, before I get to how that's been addressed, I just want to clarify what I mean. When we reject the null hypothesis, what we're basically saying is that there does seem to be something here. Remember what a null hypothesis is. A null hypothesis is a prediction that there is no relationship, there is no significant difference. So if we reject that, we're not really saying what we found. All we're saying is it's not nothing. You know, we found something, but it's not any more clear than that. We're not being very specific about exactly what it is we found here. So one of the standard techniques that we use for dealing with that inherent, you know, lack of information that null hypothesis testing produces is to follow up that hypothesis test with additional statistical procedures, like measuring effect size, for example. So after you find your, p-value, after you determine if you have statistical significant effect, then you move on to calculate things like Cohen's d or Pearson's r to see how strong that effect is, to see how, large that effect is. So by doing these kinds of follow-up, measurements, you're getting more information to the reader, you're providing a lot more context to the reader, and you're allowing them to just better be able to evaluate the data that you have in fact collected.